Hello and welcome to GCSE Particle Model of Matter topic with Mrs. Castanera. We are on lesson 9, the specific latent heat. Our keywords for today are latent heat, fusion and vaporization. So let's highlight those. Here we have the specification from the exam board, which takes up most of page 16, as you can see, and summarises what we're going to be able to do today. Our first task on page 17 is the knowledge check questions. So pause the video whilst you answer those questions now, please. Using a pen in a different colour to the pen you wrote your answers in, let's go through those. So question 1, identify the unit of specific heat. So it's joules per kilogram per degree Celsius. If you got that right, give it a tick. If not, make sure you write in the correct answer. Question 2, define specific heat capacity. So the specific heat capacity of a substance is the amount of energy that is needed to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So you need to have written the part that I'm highlighting here. So it's the amount of energy needed to raise the temperature of 1 kilogram of it by 1 degree Celsius. If you've got that right, please give it a tick. If not, please fully correct the answer by writing in the correct answer, either in the spaces around this or on the notes page. Question 3, identify the unit of density. So that's kilograms per meters cubed. And this must be a 3, this superscript letter. Question 4, name the Greek letter to signify change. So delta, so if you've written delta, you can have the mark, but you also need to write this triangle symbol. We can also write it like this. So this is the capitalized version of delta, and this is the lowercase version of delta. But both the delta, and in this case, we're going to be using the triangle or capitalized version of the letter. Question 5. What are the 3 basic states of matter? Well, they are solid, liquid, and gas. 1 mark for all 3. When it says 3 basic states, we do not want to include plasma in that. So if you've written plasma, it is wrong. Question 6, make M the subject of the delta E equals mc delta theta equation. So that is M equals delta E divided by C multiplied by delta theta. And then make C the subject of the same equation. So that is C equals delta E divided by M times delta theta. So similar equation, just M and C are replaced with each other. Question 8, what are the units of temperature? Well, it is degrees Celsius or degrees C. If you've written Celsius, that's also fine. Okay, so moving on. Oh, give yourself a mark out of 8 before we move on. So today's lesson, we're going to be looking at, we're going to consider the energy changes in a change of state, and we're going to define specific latent heat. So, changing state. Before a solid can change state, it must be given some energy. Okay, can you remember why this is? Okay, so it needs to be given some energy to enable it to make or break bonds. So when there is a change of state, remember there is no change in temperature. So this is really, really, really important. So there's no change in temperature when there is a change of state. For example, a kilogram of ice at 0 degrees Celsius will change into 1 kilogram of water at 0 degrees Celsius, and it will require 340,000 joules of energy to transform state. The energy change to transform state is called latent heat. Okay, and that's from the Latin latere, to lie hidden. And that's because it's hidden or does not manifest itself as a change in temperature. It's internal things that are happening inside, between the atoms, that are making the difference here, which is the bonds between the atoms being broken or made. So our checkpoint question here is describe how the internal energy and temperature of a substance changes when a change of state occurs. So how does internal energy and temperature change when a change of state occurs? So pause the video whilst you answer that question, please. Okay, so let's go through that. So first of all, heating increases the kinetic energy of the particles. Okay, so that increases the total internal energy of the substance. Now, the reason it increases the total internal energy, because if you remember, total internal energy is equal to the kinetic energy as well as the potential energy of all the particles. So the temperature does not change, so it's important that we write that. Temperature does not change as all the incoming heat energy is being used, so all the incoming energy is being used to break the intermolecular bonds between the particles. Okay, so there's quite a lot to this. You can have 2 marks. One for saying that all the energy is being used to break the bonds between the particles, and the phrase is the intermolecular bonds. Okay, and the other one is for saying that the kinetic energy of the particles is increased, or that the total internal energy is being increased. So make sure you say those 2 things, as well as the fact that the temperature does not change. So if you pause it to make sure you've got all this written down, that'd be wonderful. Okay, so we're going to move on. Now, there's talk of cooling curve of stearic acid, which we have looked at. So what we've looked at previously was the heating curve of stearic acid from solid to liquid. This time they're talking about a stearic acid in the liquid state. So what you might want to do here is this clip here is a video clip of stearic acid being cooled along with the resultant cooling and heating curves. So what's happening in this video is a thermometer or temperature probe is connected to a data logger placed in the stearic acid, and the temperature of the stearic acid is recorded as it cools. And you just observe what happens to the stearic acid as it changes from liquid to solid, which does take a while. So watch this, okay, have a look at it and see what you think of it. So pause the video whilst you go watch that and then come back. Okay, so welcome back. Hopefully you've watched the video by now. So using the information that you've just seen in the clip and your knowledge of water, remembering that water has a melting point of 0 degrees C and a boiling point of 100 degrees C, construct a cooling and heating curve, a cooling curve for stearic acid and a heating curve for water in the graphs below. So here are the graphs that we want you to do. So this one is a cooling curve of stearic acids. So we want you to look at going from liquid to solid. So just one change of state there. With the heating curve of water, we're going to be starting out with ice. So we're going to start with solid, moving on to liquid, and then moving on to gas. So there's 2 changes of states for this one. Okay, so pause the video whilst you do that, please. So this would be the cooling curve of stearic acid. So we have quite a rapid cooling phase, and we can label that, so rapid cooling phase. Then we have this straight section here, and hopefully you've identified that what's happening here is a change of state, and that happens at around about 55 degrees Celsius. Okay, so we're changing state here from liquid to gas. Sorry, from liquid to solid. And then we have a slower cooling curve as it continues to get cooler, but gradually slower and slower and slower. Okay, so we can just label this as a slower cooling phase. And that will continue until it gets to room temperature, which is going to be around sort of 20-25 degrees Celsius. Okay, so well done if you've got that correct. Change or correct anything that you haven't got right. I recommend you add the annotations if you don't have those. So here we have the heating curve of water, and it's getting heated, or it's warming. And the first change of state happens around about 0 degrees Celsius, which is going to be from solid ice to liquid water. So you can write along here if you like what state we are at. So we've got solid ice. Ice is a solid. Then we've got liquid water here. And as we get towards 100 degrees Celsius, we have another change of state. And then we have a gas, which in this case would be steam. So make sure you've annotated that. Tick if you've got it correct. Okay, so we're going to move on then. So, specific latent heat. The energy, 340,000 joules per kilogram, required to change 1 kilogram of water, 1 kilogram of ice to water at 0 degrees Celsius is called the specific latent heat of fusion of water. So, the specific latent heat of fusion of water, it's a long name for it, is basically how much energy is needed to change 1 kilogram of ice to water at 0 degrees Celsius. Now, different materials have different latent heats. To change a kilogram of water to a kilogram of water vapour requires 2.3 million joules per kilogram, and it's called the specific latent heat of vaporization of water. So, to go from water to water vapour, okay, that is the specific latent heat of vaporization of water. So, vaporization is clearly about changing from liquid to vapour or to a liquid to a gas, and fusion is about changing from a solid to a liquid. So for any change of state, we have a specific latent heat, and specific latent heat is defined as, okay, so specific latent heat is the amount of energy required to change the state of 1 kilogram of the substance, any substance, with no change in temperature. And we can write it out as a sentence, or we can turn it into an equation, as we can with many things in science. So the energy to change state is the mass times the specific latent heat. And we use E for energy, M for mass, and capital L for specific latent heat. And there are units for this, as you can see. So energy is in joules, capital J, mass is in kilograms, and specific latent heat is in joules per kilogram. Okay, so as we already stated earlier, specific latent fusion is a change from solid to liquid. And the specific latent heat of vaporization is a change of state from liquid to vapour or gas. Okay, you will need to learn these two statements. Okay, so there's quite a lot to learn here, in fact. Let's have a look at that. So, essential knowledge to learn is this definition in both word format and in numerical format. So, learn this. And these two definitions here for what specific latent heat of fusion and vaporization are. You will also, even though it's not included in here, you'll need to know the units for each of these. Okay, so there's quite a lot there to learn. So I recommend you spend some time learning that. Okay, and then what I'd like to do is pause the video once you've done that and answer these two checkpoint questions, please. So pause the video, learn those things as best you can. Feel free to use the notes page to help you, and then answer the two checkpoint questions. Okay, so let's go through those. Checkpoint question 1, define specific latent heat. So it's the amount of energy required to change the state of 1 kilogram of the substance with no change in temperature. You need to be saying that pretty much exactly to get the mark, because that's what we've learnt. Question 2, the second checkpoint question, what's the equation for the energy required to change state, and give the appropriate units. So energy to change state equals mass times specific latent heat, and the units are included. Joules for change of state, mass is kilograms, and specific latent heat is joules per kilogram. So you have a mark for each of those. So give yourself a mark out of 4 there, please. Okay, so moving on to page 19, there are a number of questions here. Questions 1 to 4, well 1 to 5 in fact, they get gradually more difficult, so you'll find them harder as you go on. Question 5 is extra difficult. Okay, if you can't do it, don't panic, and then we will go through those. So have a go at those whilst you pause the video. Okay, so let's go through those. Question 1, name the units for energy and mass. So energy is measured in joules, capital J, and mass is measured in kilograms, kg. So we've marked for each of those, so that's out of 2. Question 2, use the following phrases to complete the sentences. Latent heat of fusion, specific heat capacity, latent heat of vaporization. So when heating a substance without a change in state, the energy required depends on the specific heat capacity. You get a mark for that. If a liquid changes into a gas or vice versa, the energy required depends on the latent heat of vaporization. Have a mark for that too. If a liquid changes into a solid or vice versa, the energy required depends on the latent heat of fusion. So there are 3 marks for this question. Question 3. The official latent heat of fusion of ice turning into water is 336,000 joules. So that's the latent heat of fusion of ice. So ice turning into water, that's 336,000 joules per kilogram. So if you had 5 kilograms of ice, how much energy would you need to melt it all into water? And remember, here's the equation you will need. So hopefully you have done the following. You've written the equation out, which will give you a mark. You have put in some numbers, which is 5, because 5 kilograms in mass multiplied by the latent heat of fusion, which is 336,000, and that got you an answer of 1.68 million joules, or 16840 joules. Another way of writing this is 1.68 megajoules. Okay, either of those is fine. That's a great second alternative for those 2 marks. Okay, question 4. It takes 11.3 million joules to heat 5 kilograms of water. Let's highlight these key points. So it becomes steam. Can you use this information to work out the latent heat of vaporization of water using the equation? Okay, so use the equation, E equals m times L. You'll need to rearrange it so that L equals E divided by m for a second mark. Then L equals 11.3 million, or 11.3 and then 5 zeros, divided by 5, because it's 5 kilograms of water. And your answer is 226,000 joules per kilogram. So that is a mark out of 5. And our previous question was a mark out of 4. Okay, so moving on. So this is the extra difficult question. If you didn't get it, don't worry, that's absolutely fine, but I will explain it for you. So if you have 10 kilograms of ice at 0 degrees C and heated it so it melted and went up to 100 degrees and then boiled it, how much energy would that take in total? So you're melting it and you're boiling it. And the latent heat of fusion, you've given here. The specific heat capacity of water, you're given here. And the latent heat of vaporization, you're given here. So you'll need to take all 3 of these values and apply it. So let's see how we do that. So first of all, we can use the equation for the latent heat. So the energy required is the mass multiplied by whichever latent heat you're doing. And in fact, we're doing both. You may have done it as 2 separate equations and added them together, or you might do it together like this. Either is fine. So you get a mark for using the equation. Then you get a mark for putting the numbers in. Okay, so 10 is the mass, because it's 10 kilograms, multiplied by the latent heat of fusion, added to the latent heat of vaporization, which is going to be 2.6 million joules, or 2.6 megajoules. Okay. Then we need the specific heat capacity of water. We need to apply that now. So the energy required for the water, or the change in energy of the water, is the mass times the specific heat capacity times the change in temperature. So that, you get a mark for using the equation, is going to be 10 times 4,200, which we're given here, multiplied by 100, because it's going up to 100 degrees C from 0. That's our temperature change. Then that gives us 4.2 million joules, so mark for the units as well. So you've got 3 marks for this section and 4 marks for this section. So finally, we are going to add those 2 together, which is going to give us a total of 6.8 million joules, or 6.8 megajoules. There's another 2 marks here. So that is out of a total of 9 marks. Now don't worry if you didn't get any marks or if you got a couple of marks for this, that's absolutely fine. If you got stuck, please feel free to ask your teacher or email me. We're very happy to help you with this. So for this entire page of questions, it's marks out of 23. Now, if you've got 15 or more, then you're doing very well indeed, because the last one was rather tricky. Okie dokie. So we're going to move on. So unfortunately, the next activity is actually measuring the latent heat of fusion of water, which is a practical activity, and we can't really do that because it's not designed to be done at home. And that carries on to the next page, on page 21, and again on page 22. So we're going to move directly on to the conclusion, the knowledge check after the conclusion on page 22. So if you want to answer the questions, pause the video whilst you do that, please. So let's go through those questions. Question 1, describe the temperature at the change of state. Well, temperature remains the same, so tick that if you got it right. Making sure you're marking in a pen of a different colour and making corrections as we go along. So make L the subject of the E equals mL equation, so that's L equals E divided by M. Question 3, name the unit of specific latent heat, that is joules per kilogram, so that's a slash between the two, or a forward slash, which means divide. Question 4, during fusion, what happens to the bonds between particles? Well, the bonds are broken, which allows the particles to move about more easily, but as long as you said the bonds are broken, that's absolutely fine. Question 5, during vaporization, what happens to the bonds between particles? Well, again, the bonds are broken, allowing the particles to move about more freely. So it's the same thing, they're broken, just all of them are broken at this point, rather than some of them during fusion. Question 6, identify the type of energy which changes during a state change. That would be kinetic energy, and because kinetic energy changes, the internal energy also changes too, because internal energy is the sum of the kinetic energy and potential energies. But if you've written kinetic energy, that is absolutely fine. Question 7, identify the unit of specific heat capacity, so that's joules per kilogram per degree Celsius. Question 8, name 3 subatomic particles, that's protons, neutrons and electrons. You need all 3 for the mark. And question 9, what subatomic particles are found in the energy levels? Well, that would be electrons. So give yourself a mark out of 9 for those, please. Okay, so if you've got 8 or 9 out of 9, well done, that's excellent work. If you have 5 or less, that's not great. You need to have another go at that. There's some definitions or some basic explanations and understandings you need to still grasp. So email your teacher or myself if you're stuck on anything, or if you're not sure, or if you've not done especially well on that. I recommend reviewing the lesson and checking in particular things like units and definitions of what happens during fusion and vaporization. Okay, so the final task before we move on is on page 23, we have the keywords, which is latent heat, fusion and vaporization, which you should already know from the lesson, but they are there if you want them, and you should know those. So lastly, you need to watch the lesson summary video, which you can type this in, or you can get a copy of this, digital copy of this, which you should all have access to, either through the online learning page or through the school's online learning portal. And you can click on the link. Feel free to email your teacher if you're stuck or need any help with anything. Thank you very much.